Hello everyone. Let me start with a question. When you keep a bottle of soda open, why does it go flat after a while? Or why does the smell of perfume spread quickly across the room but then seems to stop changing? The answer lies in a powerful concept: equilibrium.
In chemistry, equilibrium occurs when the forward and reverse reactions happen at exactly the same rate. Imagine reactants converting into products, while at the very same time, products are turning back into reactants. The result? Their concentrations remain constant, even though molecules are still reacting. This balance is called dynamic equilibrium. For example, in a general reversible reaction, written as A plus B double arrow C plus D, equilibrium is reached when the rate at which A and B form C and D is exactly equal to the rate at which C and D revert to A and B. What looks still at the macroscopic level is actually a hidden dance of particles at the microscopic level. Let's go deeper into reversible reactions. When a reaction starts, the forward process dominates because there are plenty of reactants. But as products accumulate, the forward reaction slows down and the reverse process begins to accelerate. Eventually, the two rates become equal and the system reaches equilibrium. Here's the fascinating part. The same equilibrium can be reached whether you begin with just reactants, just products, or even a mixture of both. For instance, consider the synthesis of ammonia. Nitrogen gas plus 3 molecules of hydrogen gas form 2 molecules of ammonia gas, written as N2 gas plus 3. H2 gas gives 2 NH3 gas. At equilibrium, the mixture contains unreacted nitrogen, unreacted hydrogen, and ammonia, all coexisting in constant proportions. Now, how do we know equilibrium is dynamic and not static? Scientists use clever experiments. One way is with isotopes, but even in a classroom, we can show this with colored water. Imagine two measuring cylinders connected with glass tubes. Start with one filled with purple colored water, the other empty. When you keep transferring the water back and forth, eventually the water levels in both cylinders become constant. But molecules are still moving between the cylinders. This is exactly like equilibrium. Concentrations remain unchanged, yet molecules continue to move. In chemistry, this means that even when nothing appears to change in a reaction mixture, reactant and product molecules are continuously exchanging. Now let's talk about one of the most important industrial processes, Haber's synthesis of ammonia. In this reaction, nitrogen gas reacts with hydrogen gas under high pressure and temperature to form ammonia. At first, the concentration of ammonia increases steadily, but after some time, its concentration levels off, even though nitrogen and hydrogen are still present. This shows the system has reached equilibrium. Interestingly, the same equilibrium composition is obtained whether you start from nitrogen and hydrogen or directly from ammonia that decomposes into nitrogen and hydrogen. The balance is maintained by the rates of the forward and reverse reactions being equal. That's why chemical industries optimize conditions of temperature and pressure to shift equilibrium in favor of producing more ammonia while still respecting the dynamic balance. Here's a fascinating experiment that proves equilibrium is truly dynamic. If we replace hydrogen with its isotope deuterium, written as D2, in ammonia synthesis, the products are no longer just NH3. Instead, you get molecules like NHD2 and even ND3, all mixed with normal ammonia. This happens because atoms are continuously exchanging places even after equilibrium is reached. A mass spectrometer confirms this mixing. If equilibrium were static, only one type of ammonia would form and stay constant. But since the isotopic forms keep appearing, it's clear that forward and reverse reactions never stop. This is powerful evidence that equilibrium is not a frozen state. It's an ongoing, invisible molecular shuffle. Let's consider another classic example: The formation of hydrogen iodide. Hydrogen gas plus iodine gas gives two molecules of hydrogen iodide gas, written as H2 gas plus I2 gas gives 2HI gas. If we start with only hydrogen and iodine, the concentration of HI rises until equilibrium is reached. On the other hand, if we begin with pure HI, it slowly decomposes into hydrogen and iodine until the same balance is established. Graphs of concentration versus time show how the levels stabilize. This proves that equilibrium can be reached from either direction, and the final composition depends only on the conditions of temperature and pressure, not on how you started. Let's summarize the key takeaways. At chemical equilibrium, the rates of forward and reverse reactions are equal. The concentrations of reactants and products remain constant with time, even though both reactions continue at the molecular level. Importantly, equilibrium can be reached from reactants only, products only, or any mixture of the two, and the final state will always be the same under given conditions. This balance does not mean the reaction has stopped. It means a dynamic state of equal push and pull has been established. So, equilibrium is really about balance in rates, not equality in concentrations. So to wrap up, chemical equilibrium is not the end of a reaction, it's the beginning of a balance. From ammonia synthesis in giant industrial plants to the fizz in your soda, equilibrium explains why reactions seem stable yet are alive at the molecular level. I hope today's session helped you see the hidden dynamism behind chemical equations. Chemistry is not just formulas on paper, it's an active dialogue between atoms and molecules. Catch you in the next class where we'll uncover even more fascinating laws that govern equilibrium.